So we have two speakers online today. The first speaker from Germany is Ole Koenig, Anglophonically pronounced. So he's currently fourth year graduate student working on X-ray binaries with Professor Jon Wilms at the Raimeis Observatory in Bamberg, Germany. He studies black hole binaries using spectro-timing methods and the early mission stage of novae. Through the Erosita consortium, he led a great discovery of a nova in the fireball phase, which is mentioned in the title in the Nature paper, as you saw. He's currently also part of the 60 end-to-end simulation team in the ARENA, WFI, and the XI consortium. So the title of his presentation, if you can please share the screen only. Perfect. The title of the presentation is X-ray detection of a nova in the fireball phase. And with that, no, okay, sorry, just a second. Yeah. Okay, yeah. Okay. I hope it's visible enough, but we definitely need to turn off the lights. Okay, now it's better. Okay, with that, Ole, the floor is yours. Thank you.
Thank you very much. Yeah, thanks a lot for inviting me to give this talk, and greetings from Germany. I would like to present the X-ray discovery of a nova in the fireball phase with Erosita. Let me start with an introduction to novae. These objects have been around for quite a while. The first recorded nova was about 2,000 years ago by Chinese astrologers. And then in the 1950s, it was realized that these systems are in a binary system, and they consist of a white dwarf and a donor star, and they are in gravitational interaction, circling around each other, and then mass accumulates on the surface of the white dwarf, and a shell of mainly hydrogen builds up. And this shell becomes hotter and hotter and denser and denser. And at some point, the temperature and the pressure is so high that thermonuclear fusion can ignite via the CNO cycle. And that leads to a rapid burning, a thermonuclear runaway that propagates around the whole white dwarf and then quickly diffuses through the layers of this envelope to the top. And at this stage, this fireball, this hot glowing white dwarf is so hot, 10 to the 7 Kelvin, that it shines in the soft X-rays. So this phase should be observable as a short and a very soft X-ray transient, radiating at the Eddington luminosity. The further succession of the events is that this whole thing explodes. So the envelope expands, and because it expands at constant luminosity and with an increasing radius, the temperature drops. So the peak of this black body spectrum, this Planck spectrum, is shifted into the optical. And this is the main way how these novae are found. A handful of novae in our galaxy every year. And they are usually found just as it was 2,000 years ago, because suddenly a bright spot is in the sky at a position where it was not previously. And now this is already the crux of the problem of detecting the X-ray flash, because at the stage of the discovery, usually of the optical increase, the X-ray flash is already gone. And that's the reason why it hasn't been found yet, although there were dedicated search campaigns. And then later we find a whole a huge variety of radiation from the electromagnetic spectrum. We have gamma rays, which originate in shocks when shells of different velocity crash into each other. There is hard X-ray emission, and then the super soft source phase where we have residual thermonuclear burning. And this is also very well known, but this X-ray flash has not yet been found, this very first stage of the explosion, of the outburst. But why is it so interesting to find it? Well, firstly, the theoretical work on these X-ray flashes and on the outburst characteristic goes back to the 1990s. So this would also confirm just a lot of theory, which would be nice, of course. But it can also tell us something about the physics. It can help us constraining the timing of the thermonuclear runaway. When exactly does it happen with respect to the optical peak? It can help constrain the amount of material that was in the system. You can imagine if a huge explosion blasts through the system, then the complete environment is changed. So at the time of the X-ray flash, we still have this original system, and by studying the absorption, we can say something about how much gas is in the binary system. We can say something about energy conservation, because throughout the outburst, the energy should be conserved, right? Ideally. And then it can also help us constrain the white dwarf mass, which is a quite difficult thing to do, to get the white dwarf mass. In this diagram here, you see the time on the x-axis in logarithm of years, and on the y-axis, the temperature of the photosphere. And you see that only the most massive white dwarfs have an X-ray flash. This is indicated by this band here. The white stuff is in the X-rays because the temperature is high enough. And the first peak here corresponds to the X-ray flash. And it's much shorter for the heavy white dwarfs. So that means if we get the duration of the flash, we can estimate the mass of the white dwarf. And that brings me to the Erosita mission. I hope you've all seen this beautiful image of the first all-sky survey. Erosita is an all-sky mission. It scans around its own axis and scans a part of the sky every 4 hours. And then it revisits this part every half year. So we get multiple scans 4 hours apart. And during one of these scans, something very peculiar showed up. What we saw was this. We saw an eye that was rimmed with fire, but was itself glazed, yellow as a cat's, watchful and intent. Well, almost. What we saw was this. We saw an extremely bright transient that was not there 4 hours previously. 4 hours in the scan, 4 hours before this event, there were just a couple of background photons, then this enormously bright transient, and then again, nothing 4 hours later. In fact, the transient was so bright that it saturated the central part of the detector. So this is what you can see here as this depression and brightness in the center. And just to show you that we really discovered the Eye of Sauron just convolved with the detector response, I'm gonna switch back and forth here. Let's have a look at the temporal evolution of the event. So in this light curve, you see the days after the event, and in red, the count rates of Erosita with this very, very bright outburst during the one scan, and in blue, the optical data. And you can see that at the time of the X-ray flash, we did not yet have an elevated optical flux. Only half a day after the event, after the X-ray flash, we see this massive increase in the optical by several orders of magnitude. And then it still rises to about 3.7 magnitude. So this is really bright. This is visible by the naked eye. And then 5 days after the X-ray flash, the event starts decaying. We also find gamma ray emission, and then later the super soft phase. So this very, very nicely matches this theoretical picture of the outburst. So great, we have this super cool transient, but really the problem that we have is that it is so bright. We get detector effects that are highly nonlinear, and they are summarized under the name Pileup. Pileup occurs in two different ways. There's pattern pileup, which means that so many pixels get illuminated that invalid patterns emerge, and they are disregarded because the reconstruction algorithm thinks that they're invalid. So this is why we get this loss of signal in the center. But that would be not so bad because we have a lot of counts anyways. The really severe problem is the energy pileup. Energy pileup means that two photons hit the same pixel during one readout cycle. And that means that we can't distinguish if this is from two photons or from only one. And this shifts flux to higher energies. This is why the spectrum gets distorted. And this is why we can't just go ahead and fit our favorite model to it. And we can't even infer the flux of the source. So yeah, this is a really big problem. And the way how we move forward with this is to use 60. 60 is a simulator that can be used to simulate X-ray telescopes. That's the name, simulation of X-ray telescopes. It is what is called an end-to-end simulator. So it goes all the way from the astrophysical source through the optics and then simulates the readout process. It takes the vignetting, the point spread function into account, the interaction of the photons in the semiconductor, so the charge cloud. And here, most importantly, we take the pileup into account. So this is an ideal an ideal case to simulate this highly piled up observation. And in this little animation that I think you can see it much better here. Let's switch to here. Oh, maybe not. Okay, what you see is that we can run simulations for different source fluxes and different spectral parameters. So let's say we have a black body and then we change the temperature and the flux, and we then minimize the observation against, we minimize the simulation against the observation just by chi-square minimization. And this way we can reverse engineer the intrinsic spectrum of the source. We derive at a pretty good fit, and we can describe the spectrum indeed with a black body with a temperature of roughly 30 electron volts. And I again want to emphasize that this whole difference here in flux, this is all due to pileup. And yeah, this is accounted for in the modeling. And this way, by simulating it, we can get hold of the flux as well, which was roughly 1 Crab, which is really, really, really bright for Erosita, and the absorption as well. Great, so you made it through the most tricky part, through the analysis. Now let's start the interpretation. What can we say about this system? We have this white dwarf. There is a thermonuclear runaway process somewhere in the atmosphere, and then it propagates to the top of the envelope. That takes between 5 and 10 minutes. And then the envelope starts to expand, and it expands and expands, and it expands further. It does that quite quickly to 10-fold the radius, to go from 1 white dwarf radius to 10 white dwarf radii. It takes between 10 seconds to 1 hour. So this is an extremely dynamic event. And we think that we observed the source at this stage, when the radius of the photosphere was about 50,000 kilometers. So for reference, the radius of a white dwarf is between 2 or 3 and 15,000 kilometers, or the size of Earth roughly. So this is about 10 times the size of the white dwarf. But given the really quick acceleration and expansion of the envelope, this is still very, very, very close to the surface of the white dwarf. We find a temperature of 30 electron volts, which very nicely matches with the idea that we are in the decay phase when this envelope expands and cools down. And it indeed radiates at the Eddington luminosity. And what I mentioned in the beginning was that we can derive something about the mass of the white dwarf from the duration. So we have one detection, which the scan was 36 seconds. This is all the data we have, 36 seconds. And then 4 hours before and 4 hours later, we have a non-detection. And that means the flash must be below 8 hours. And with this, we can already do quite a lot. And in a study that came out a couple of months after our paper, Kato et al. Analyzed the observation and plotted synthetic light curves into the time frame that our detection gives. So we have our detection here marked as the dot, and then the green arrows are the upper limits of the non-detections. And by looking at many different models for different white dwarf masses, we can deduce something, we can derive the white dwarf mass, and it turns out to be quite close to the Chandra-Sekhar limit, which is interesting because there you start approaching the region where you approach supernova type 1a events. And another thing that comes out of this analysis was that this envelope that expands, there are winds that are launched from the photosphere, and they are launched with different speeds. And the inner wind, the wind that comes later, is much faster. So it crashes into the inside of the expanding shell, basically catches up and creates a shock, and this leads to the gamma ray emission. And what they derived was that this wind must be optically thick, and the X-ray flash terminates when the wind is launched. So this can also tell us something about the wind launching mechanism, which is very exciting. And with this, I'd like to conclude. I would like to conclude with the quote that I found in a paper that was written more than 30 years ago. And it says it is possible that an X-ray flash could be detected by a very sensitive all-sky survey. And this sensitive all-sky survey is Erosita. Erosita that detected the first X-ray flash from a nova. And the second take-home message I would like to convey to you is that heavy and even severe pileup can be accounted for with 6D modeling. And with this, I'd like to thank you for your attention, and I'm happy to take any questions if you have any.
Thank you so much. Do we have any questions from the audience in person? Yeah, try if you don't hear all, let us know and repeat the question. Or if you want to repeat it. Yeah.
Hi, really cool work. Questions about timing. So you said that each Erosita, Erosita observes any given patch for 4 hours, right? But you were able to show this particular spot at 3 intervals that are spaced 4 hours apart. Like, at least the way you said it, it seemed to me that the telescope would have started looking in a different direction 4 hours later.
Maybe I should have made this a little bit more clear, the survey strategy of Erosita. So Erosita is in L2 and it scans great circles. So it spins around its own axis every 4 hours through the ecliptic North Pole and the ecliptic South Pole. So every 4 hours, it does one of these circles. And then because it moves around with the Earth, around the sun, all of these great circles, they are always a little bit shifted with respect to each other. So you always get, you never scan exactly the same patch of the sky, but always a little bit shifted because Erosita moves around the sun. And then at some point it gets out of the field of view. So usually it depends a little. So the sources that are at the North Ecliptic Pole, like the LMC, then, or is it the South Ecliptic Pole? Well, at the Ecliptic Pole, the Magellanic Clouds are located, and then you get every scan, you get basically one detection. But if it's in the ecliptic, you only get a couple scans, maybe 6, and then Erosita moves out of the field of view. The source moves out of the field of view.
Thank you. And sort of a similar thing about where you say that the fireball grew between, like, over the course of 10 seconds to 1 hour. Like, how do you constrain those time scales?
Yeah, this is quite tricky. It highly depends on it very much depends on the accretion rate, and so the how much material is accreted, how much actually mainly the composition of the white dwarf and the mass of the white dwarf determines this factor, and then you can get this out of theoretical models that calculate this thermonuclear runaway.
Mm. Okay, thank you.
How many more of these is Erosita likely to see in its lifetime?
Yeah, good question. So far, we've seen one. Erosita is in safe mode right now. So let's see. But we have tried to estimate the number of events given the galactic nova rate, which is about 50 per year. Note that only a couple of them are actually found because they can also be attenuated by gas. And we derived a number of 1 to 2. Depends also on the duration of the flash. We know it's shorter than 8 hours, but if it's only 1 hour long, that would lower that number. If it's 6 hours long, then the number would be higher. But yeah, it's not a lot. Yeah, we can definitely wait for Einstein probe because it has this large large sky coverage, and with Einstein probe we will hopefully be able to see more of these events.
More questions from you? No. Any questions from the audience on Zoom? I don't see any. So let me maybe ask a question. So you showed the Erosita spectrum, which I guess was time integrated over a certain interval, and also a very nice follow-up with Fermi. So how can you tell, or can you tell how the high energy tail of the Erosita spectrum is connected with the X-ray emission which you see afterwards? So is there any genuine high energy X-rays coming from Erosita, or that's only thermal, and the gamma rays due to the energetic particle come quite some time afterward?
Yeah, that's a really good question. So the spectrum that we derive is purely thermal. We really see this hot glowing fireball. And there's very, very little flux above, like here at 1 keV, basically we see nothing, but then keep in mind, this is also piled up. So the intrinsic spectrum cuts off even lower. The Fermi, the gamma rays, they are produced later from particle acceleration in shocks. So when these different winds are launched and crash into each other, then we get particles accelerated and they will decay and produce gamma rays. But this is a different mechanism.
Yeah, so you cannot say if earlier than prior to the 5 days there were any accelerated electrons there. You just cannot say, right?
We don't see any, no. I mean, at the time of the X-ray flash, we see no enhanced gamma ray flux.
All right, thanks.
Which makes sense if because it takes time to launch these winds.
Yeah. Thank you. No more questions? No, okay. So let's switch to the second speaker. Roberto, if you can start sharing your screen.
Yes.
While I introduce you. So our second speaker is Roberto Gilli. He's a senior researcher from the INAF Institute of Natural Astrophysics in Bologna, Italy. He received his master's degree in astronomy from Bologna University in 1997 and then PhD in Florence in 2001. Afterward, he was a postdoctoral fellow at the Johns Hopkins University in Baltimore, and then returned to Florence. And in 2005, he moved to Bologna as a researcher. So his research interests includes the physics of the physics and the cosmic evolution of the accreting supermassive black holes. He has a long-term experience on the deep X-ray service of the AGN with Chandra and XMM. Also AGN population synthesis models of the cosmic X-ray background, AGN obscurations and demographic. Is involved in development of the science case of the next generation of the X-ray facilities like StarX, Axis or Athena, that are supposed to discover the most distant and hidden supermassive black holes. His title today is The Cosmic Evolution of the Interstellar Medium Density and its Role in Hiding Early Supermassive Black Holes. Thank you, Roberto, and the floor is yours.
Thank you. Thank you very much, Federico, Shuriana, and all the organizers for inviting me. It's a pleasure to give this talk at the CFA remotely, even if remotely. So today I'm presenting the results from a recently published paper in Astronomy and Astrophysics. It's about the cosmic evolution of the interstellar medium density and its role in hiding early supermassive black holes. And as you can see from the title of the paper, essentially the conclusion is there. So the conclusion of the talk will be that most supermassive black holes at high redshift are likely to be heavily obscured by the interstellar medium of their hosts. So let me go straight to the problem. So what we normally see from the inventory of X-ray selected AGN in deep X-ray surveys, the most famous X-ray surveys like the Channel South, North, Cosmos, and so on, is that most of the accretion onto supermassive black holes occurs during hidden phases where large amount of dust and gas hide the direct view of the nucleus. But not only, it is also quite firmly established that the fraction of hidden AGN is increasing strongly with redshift. So in this plot, you can see an example of this result from a paper by Fabio Vito, where you see the obscured AGN fraction versus the X-ray intrinsic luminosity of the sources. And you see that at threshold 0, you measure something that is on average about 20%, whereas when you use the results from the deep X-ray survey and you are able to sample redshift above 3, so in this case, the average redshift of the population is 3.5, you do see that the obscured AGN fraction at any luminosity is something between 60 and 80% of the total. So the reason for this increase of obscuration is largely unknown, and then this is what motivates the study I'm presenting. So one possibility that one may think of is that the covering factor of the circumnuclear medium around the black hole, the one that is distributed on parsec scale, and that we believe normally it is distributed like a torus around the black hole. So one possibility is that the covering factor of the torus gets larger as you go up with redshift. So this is a possibility, but maybe this is not really the reason for the increase we do see in the obscured fraction. Because, for instance, this argument that is shown in this slide may tell you that the covering factor of the small-scale obscured material does not evolve with redshift. So in the left panel, you do see the spectral energy distribution, the broadband spectral energy distribution of quasars. You do see the classic 2 bumps in the ultraviolet and in the mid-infrared. And normally, you could use the strength of the mid-infrared emission, which is believed to be reprocessed ultraviolet emission from the torus. You can use its strength relatively to the strength of the ultraviolet intrinsic emission to gauge the torus covering factor. Obviously, the larger it is the process fraction, the larger is the covering factor. So when you do this game, when you try to compute the ratio between ultraviolet and mid-infrared luminosity as a function of redshift in bright quasars, for instance, in Sloan quasars, you do see, as shown in this right panel, that this ratio is essentially constant with redshift, and the luminosity of the objects in these beams are roughly the same. So we are sampling objects with equal luminosity, and they do appear to have the same torus covering fraction as they move up in redshift. So this simple check would tell you that really the small scale coverage of the small scale material is not changing its covering factor with redshift. Conversely, what we know is dramatically changing with redshift is likely the covering factor of the interstellar medium of the host galaxies. So there are empirical relations which have been found already a few years ago in the literature, where you do see, using primarily ALMA data, that the total ISM mass, total mass of the molecular gas, mostly in the host galaxies, increases rapidly with redshift. And this dependence, redshift dependence, is about 1 + z to the second power. Also, we know that galaxies get more and more compact as we move up in redshift. So for instance, the effective radius of a given galaxy population decreases, as you do see here, with redshift, roughly with 1 + z to the -1. So if you simply combine these two behavior and compute the mean ISM volume density, so the total mass divided by the cube of the size, you would naively expect that the total ISM density increases very rapidly as 1 plus z to the 5th power. And also, if you reason in terms of surface density or column density equivalently, you would expect that it scales like n to the over r squared. And so you would expect that it goes up again rapidly with 1 plus z to the 4th power. So it seems that this increase of the ISM density may produce the increase in the obscuration fraction we do observe, but we wanted to demonstrate this quantitatively. So what we did is taking samples of galaxies over at different redshifts. In particular, we considered massive galaxies. So we cut samples of objects with stellar mass above 10 to the 10 solar masses. And the reason is that these big objects likely have big black holes in them. And so we could see their X-ray emission up to high redshift. And also these large mass galaxies also are expected to have an ISM with the solar metallicities. And so since metals are what absorb X-rays, this is important if we want to make any consideration about X-ray obscurations. So we used samples of massive galaxies that have been observed with ALMA and that have been observed with sensitive observations down to tens of microjansky, because we wanted essentially to be able to trace dust masses in the far infrared ALMA data that have a limit of about 10 to the 7 solar masses. And this cut allows you essentially to sample or to detect more than 50% of massive galaxies at any redshift. And this allows you to make reliable correction for incompleteness. So in this plot, you do see the samples of objects we considered. There are famous samples, Aspects, Cosmos, Alpine at redshift 5. And for redshift 6, we used essentially the host of bright quasars, because at redshift 6 and above, very massive galaxies are very rare, whereas we do expect that the very bright quasars that we see in the Sloan and other surveys are hosted by massive galaxies, definitely with stellar masses about 10 to the 10. So these are all the samples we considered. And based on this sample, we used different proxies to estimate both the ISM mass, total mass, and also the effective radius of the gas distribution. Now, I will not go much into the details, you may ask me later on, but essentially we consider different traces for the mass, like the luminosity of the carbon oxide. We consider the dust mass plus a conversion factor to go from the dust mass to the gas mass. We consider also the luminosity of the carbon-2 line from atomic carbon, which recently has been proposed to be a good tracer for the total gas mass in the ISM. And similarly, we use the proxies to estimate the dimension of the extension of the gas, again, using CO, the dust continuum, the C+ line, but also trying to estimate the stellar radius through HST, mainly HST data. So here you see a summary of the data that are available for our samples. And whenever we had the C+ emission, we use that. And for the other samples, we used essentially HST plus with the size plus the dust mass to get the total ISM mass. So having chosen proxies for the gas mass and for the gas size, we assumed a simple model of the gas distribution in the galaxy, which is essentially a disk with an exponential, radially, an exponentially declining profile in the radial direction, and the constant instead the profile along the vertical axis. And under this simple assumption, the total column density that you would observe from the nucleus when average over all the directions is about 2 times the gas surface density, which you would simply derive dividing the gas mass by the essentially the gas surface. So with this scheme, we have a way to estimate what is the average surface density of gas in massive galaxies, and for the different samples, and the results are showing this plot. So here you see the column density towards the nucleus as a function of redshift for the samples I've shown before. And as you do see, moving from redshift 0 to very high redshift, the average column density essentially moves from 10 to the 21 to the 22 to 10 to the 23 or even higher. It can even reach quantum thick values when you are at very high redshift, 6, 7 or so. All the dots represent galaxies in the samples. And this shaded region here shows the region which is bounded by the median of the sample we considered. And also here, the lower boundary is the median of the samples when you do correct for selection biases. So we believe that, and this is a kind of conservative correction. So we believe that the true trend is in between this light blue area, which may be well approximated by this long dashed curve, which is is parameterized as an increase of the column density with the redshift as 1 plus z to the 3.3 power. So if we take this average region, light blue region that I've shown here, and we compare with the average column density that we measure in deep survey, or also that are derived from works that try to correct for incompleteness biases in the X-ray observation, we do see that essentially already at redshift of 2, the ISM column density becomes comparable with the average absorption we see in the AGN populations, whereas at low redshifts, maybe the ISM density falls short in reproducing what you do observe in local sample. But this already tells you that the ISM may provide a significant contribution to the obscuration of nucleus when you go up in redshift, when you go to the early universe. So after that, we try to refine our computation and work out a simple model for the ISM distribution. Particularly, we try to assume a clumpy geometry for the ISM. So we assume that the gas is distributed into clouds, and we follow it essentially the formalism that was presented in this paper. So we used number of clouds with the same mass, radius, and then surface density. This formula here, you don't have to consider the full math, but this is just to show you how we proceeded. So essentially, given our geometry, we are able to compute an average number of clouds at a given observing angle to the nucleus. This number can be also expressed in terms of the total gas density divided by the individual cloud surface density. And this quantity here is what enters in the computation of the obscured AGN fraction. So this is for a single cloud type. We also try to complicate a little bit the things and consider distributions in the cloud radii and also surface densities. So in particular, based on what we do see for the giant molecular clouds in our galaxy, we consider the Schechter functions, both for the dimension of the clouds and also for the surface density of the cloud themselves. So we assume two Schechter functions. These are the characteristic radius and the characteristic surface density of clouds in our galaxy. And we allow the characteristic surface density of the ISM to evolve with some power of redshift And so we assume that the characteristic surface density may evolve as 1 plus z to the gamma. So we allow for cloud to get denser and denser as you move up in redshift. And actually there is support, some support, observational support to this assumption based on lensed galaxies. And in particular, this system here at redshift 1, you do see that when you compare these violet points in this lensed galaxy at redshift 1 with what you see at redshift 0, essentially at equal radii, you do observe that galaxies are, clouds are more massive, which means that the density increases significantly. So again, this formalism, when put into the formula that I was describing before, allows us to essentially compute, according to this formula, what is the obscured fraction above a given cloud surface density, which is essentially about above a given NH column density. And the results of this modeling are shown in this right plot. So in the y-axis, you see the obscured AGN fraction as a function of redshift. And in blue, you do see curves in which the individual characteristic cloud density scales with redshift like 1 plus z to the second power. And the different labels refer to different column density thresholds. So for example, this blue continuous curve here shows what is the predicted trend for the obscured fraction of AGN with column density above 10 to the 22 if the characteristic cloud density increases with this power. And the red curves instead show the same thing, assuming a different slope. So a steeper increase, which essentially produces the same amount of gas with less clouds, and then the chance of hiding the nucleus becomes lower. And this is why if you have a steeper increase of the cloud characteristic density with redshift, you would expect a milder trend with redshift. So this formalism allows us to expect how the fraction of ISM obscured AGN should evolve. But we know that the ISM is obviously not the only medium that may obscure the nucleus. And actually, we know that, for instance, in the local universe, what is mostly obscuring the AGN is something that is distributed on circumnuclear scale, on parsec scale. And so we added into the formalism the contribution of the torus, and in particular, based on results, recent results from the literature, we considered that objects may have a different covering factor from the torus depending on the luminosity. So this is also well known. There is a nice result by Xu Zhao last year showing that low luminosity AGN, so CFET-like AGN, have a torus covering factor that is about 0.7. We also know that this is decreasing as you go up with luminosity, and this goes down to 0.5, for instance, for bright quasars, for instance, for Sloan quasars. So in this plot here, you do see this, some of the same curve I showed in the previous plot, and also I'm showing what is the obscured AGN fraction depending on different orientation, different covering factors. So if the half of the angle of the torus is about 45 degrees, you would expect a 0.7 covering factor. If it is 60, you expect something that is 0.5. And if you combine this constant covering factor with the ISM covering factor you showing the previous plot, you would expect curves that are these blue curves here or these red curves here, depending on how fast the average cloud density is evolving. So with all this machinery, we are now in the position to try to compare these curves with what we see in surveys. And essentially, the comparison is shown here. So all these data points are a compilation of the results from, again, deep X-ray surveys or also from works to try to compute the luminosity function of AGN at different redshifts and then try to correct for the missing population of obscured AGN. And you do see this trend of increasing obscured AGN fraction going up with redshift. In this panel, what is shown is samples of objects that are bright, 10 to the 44 in the X-ray, and as a definition of obscuration threshold here is logarithm of an age of 10 to the 22. And this behavior that you do observe may be well reproduced by this solid, thick blue curve that is the combination of the increased obscuration from the ISM, assuming this particular model, plus the small scale coverage of the torus that is appropriate for luminous system as are those considered in this figure. So the torus covering half opening angle of about 60 degrees. And this kind of modeling seems to be also in fair agreement with the data points when you move to objects of the same luminosity, but consider different thresholds for the obscuration. So in this case, the obscured fraction refers to those objects obscured with columns above 10 to the 23. And again, the model, the thick line, which shows a combination of an ISM obscuration plus a torus obscuration, assuming again 60 degrees as half opening angle, produces a fair agreement with the data. So this modeling is able to quantitatively reproduce what we do see in deep X-ray surveys. And not only at high luminosity, but also at lower luminosities, although the observations obviously are more difficult, so they are more scattered because objects get more difficult to detect. But again, such a scheme, considering what is an appropriate opening angle for low luminosity AGN, so torus opening angle of 45 degrees, half opening angle of 45 degrees, combined with the ISM evolving covering factor, gives you this dashed thick line that again is in fair agreement with the data. So in the previous plots and also in this plot here, if you extrapolate what you do see from shift 0 to 2 and go up to 6, 8 and above, you would expect that essentially 90 or even more % of AGN in the very early universe would be hidden, even sometimes even heavily hidden to our view. And the simple analytic scheme appears to be in good agreement with what people is finding in numerical simulations. For instance, this is a nice work by Yigny a couple of years ago, where you do see in this plot here the distribution of the density around black holes, and in this summary plot here, how this Koenig density should evolve in the simulation from redshift 0 to redshift 7. And again, in the simulation, it is expected that the ISM of the host is producing absorption to the level of 10 to the 23 and 10 to the 24. So these two results combined really suggest that in the early universe, maybe most of the accretion is obscured. And so if you give me just one more minute to be a little bit speculative, to the liberty of including some recent results from James Webb, this may have important implications for what we see with James Webb. You know that there are a bunch of very high redshift galaxy candidates in the first release of James Webb data. Photometric redshift can reach even 10, 12, and we are waiting for spectroscopic confirmation of these sources. And what we already know about them is that their size is very complex. So these galaxies here at redshift above 9 essentially fall in the same extrapolation of the trend observed in the local universe. So their effective radii are of the order of a few 100 kiloparsecs at most. And if you essentially compute what is the star formation rate surface density using ultraviolet emission and squeezing them in the compact region, you will see you get something that is shown in this plot here, according to which the very high redshift galaxies may have very compact regions of star formation. And again, making another assumption, assuming that these galaxies follow the Schmidt-Kellington relation, you may guess that this material, this star formation that is occurring in very compact region, is associated to gas with densities of the order of 10 to the 24 or something. So there are a lot of caveats we may discuss about. These are small mass galaxies, these are metal pool galaxies, these are blue, so little dust, but the material that they can produce star formation may be really Compton thick in density. So this is essentially my last slide, and I will leave you the conclusion saying that it is likely that the increase in the obscuration we see in AGN is produced by the increase in the density of the ISM. I believe that what James Webb and other probes will observe in the near future may test relatively well this scenario. And thank you, and sorry if I took a little bit longer than expected.
Thank you. Any questions from people in person? Oh, yeah. Sure.
I have a question regarding this conclusion about the majority of SMBHs. But how about the feedback? Because the feedback is supposed to happen at some point and push away all this ISM. So won't they clear up themselves?
Yes, this would, yes. At some point this will occur, but on average, this might occur at later times. So even at redshift, obviously, we do see quasar at redshift 6 that are unaffected by absorption. And so those systems might be those where feedback has already proceeded effectively. But for one object where feedback has already occurred at redshift 6, maybe we may expect 10 or even more where feedback has still to get in.
Thank you. Yeah.
I have a similar question to Igor's. Instead of SMBHs, driving the dense gas and dust out, what about just star formation, which is going to precede the building up of AGN in the first place? So I would think at high redshifts, whether black holes have not yet become that massive, but star formation is occurring, that there would be a significant amount of either mass loss from what is becoming a galaxy, or at least diluting it. Star formation.
I'm not sure I got it, sorry. So it's related to star formation, but I'm not sure I got the question.
Well, wouldn't the supernovae and winds from massive star formation in particular drive out a lot of this obscuration? Instead of relying on AGN, which will form later, I would think that the first thing that's going to start reducing the obscuration is massive star formation, massive stars.
Yeah. I think this can certainly occur, and also I think that this is implemented in simulations, maybe not in all simulations, but in some simulations it is. And so yet again, when you implement this feedback, this allows you to get a population of quasars that is already unobscured at redshift of 6. Otherwise, you would have expected an even larger fraction of hidden black holes.
So what about detecting these things in the radio?
That's interesting. we not at this extreme redshift, but we are trying to get them. As you may know, at the moment, we have no robust examples of hidden quasar at redshift above 5, above 6. There are a couple of candidates as shown here in the last slide. But again, these are still candidates. And so since at the moment we have been so unlucky using deep surveys, one possibility might be using radios as you were suggesting. And what essentially taking, standard radio emission in radio quiet populations, it might turn out, this is from preliminary computations we did with the student, it might turn out that radio is more efficient and may return if the sensitivity is enough. So for instance, when SKA will be operating, we return much larger number of hidden AGN than you would expect from, for instance, from X-ray selection. So radio, I think personally that might be a very promising way, because it's largely free of obscuration. It might be a very promising way to, to pick objects, to pick candidates for subsequent follow-up.
Thank you. More questions from you? No, I don't see any question online. So let's thank both our speakers again. See you next week. Thank you so much, guys.
Thank you. Bye. Thank you.
Bye.
Bye-bye.
Bye.